Hi guys. Alright, so Mr. Dempsey and I have kind of heard you guys talk a little bit about being confused about the history packet and the science packet. So Mr. Dempsey is putting together a video about the history packets, and I'm going to put one together for the science packets. Just like in my other videos, I am going to apologize ahead of time because my dog is going to start crying. But that's just because she's a baby. But that's fine. So you guys have where for science class there were about 9 NTI assignments in packet 1. However, we kind of trimmed that a little bit, so I'm not 100% certain which worksheets. I thought I had a copy, but apparently I don't. So I am going to talk a little bit about each of these and kind of go from there. Okay, so if there is an assignment, like let's say assignment number 2 you guys don't have, but I'm going to talk about it for about 5 minutes, you can either just sit and listen to me talk about science, or you could go forward a little bit. I'll make sure to say hey, I'm talking about NTS assignment number 3, or something along those lines. Okay, so NTI assignment number 1 is really straightforward. Okay, it is a web quest that focuses on air masses, fronts, weather, and precipitation. Okay, you have another document that will help you answer these questions. Okay, so you have where, if you guys go to this, we have where this is literally going to kind of take you right to our places. Okay, now the problem is you guys have a paper copy and you guys don't have this. Now, Miss Stoltz is usually she's pretty awesome, and I'm sure these links are already up. But we have where I'll kind of open them up so that way you guys can see the materials. Okay, and you can always pause if I go too fast. That's 100% okay. So if you look at the first few questions, the first 4 questions relate to weather and climate, which happens to be what our first one is like. So weather and climate are different but related concepts. Discover more. Yes, please. Now we're on this fun little website. Okay, so I'll read the website and you guys will be able to answer these 4 questions. Okay, so our 4 questions: what is weather? In which part of the atmosphere does most weather occur? What is climate? What is global climate? All right, so what is weather? Rain and dull clouds, windy blue skies, cold snow, and sticky heat are very different conditions, yet they are all weather. Weather is the mix of events that happen each day in our atmosphere. Ding, 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 ding. We have our answer 1, right? Weather is different in different parts of the world and changes over minutes, hours, days, and weeks. Most weather happens in the troposphere, the part of Earth's atmosphere that is closest to the ground. I think we might have just answered our first 2 questions just by looking at this first paragraph. The air pressure and weather. The weather events happening in an area are controlled by changes in air pressure. Air pressure is caused by the weight of the huge numbers of air molecules that make up the atmosphere. Typically, when air pressure is high, their skies are clear and blue. The high pressure causes air to flow down and fan out when it gets near to the ground, preventing clouds from forming. When air pressure is low, air flows together and then upward when it converges, rising, cooling, and forming clouds. Remember to bring an umbrella with you on low pressure days because these clouds might cause rain or other types of precipitation. Predicting weather. Meteorologists develop local or regional weather forecasts, including predictions for several days into the future. The best forecasts take into account the weather events that are happening over a broad region. Knowing where storms are now can help forecasters predict where storms will be tomorrow and the next day. Technology such as weather satellites and Doppler radar helps the process of looking over a large area, as does the network of weather observations. The chaotic nature of the atmosphere means that it will probably always be impossible to predict the weather more than 2 weeks ahead. However, new technologies combined with more traditional methods are allowing forecasters to develop better and more complete forecasts. Weather and climate. So now that we're moving into climate, let's find out what the difference is and what is climate and what is global climate. The average weather pattern in a place over several decades is called climate. Okay, so we know weather was atmospheric events, and now we know that weather patterns over decades is called climate. Different regions have different regional climates. For example, the climate of Antarctica is quite different than the climate of a tropical island. Global climate refers to the average of all regional climates. All right. As global climate changes, weather patterns are expected to change as well. While it is impossible to say whether a particular day's weather was affected by climate change, it is possible to predict how patterns might change. For example, scientists predict more severe weather events as climate warms. Also, they predict more hot summer days and fewer extreme cold winter days. That doesn't mean that there will be no more winter weather. In fact, large snowstorms might even be more likely in some areas, as less cold air is able to carry more water with which to make snowflakes. Weather is also affected by climate events like El Nino and La Nina, also known as ENSO. Climate events like these affect the weather in many areas of the world, causing extreme events like storms and droughts. So we can answer our first 4 questions from this article. All right. The remaining ones, because there are quite a few. So we have like air mass, we've got temperatures, boundary dividing the Gulf of Mexico for the weather fronts. So I will open each of these and have where they can be up. All right, so this one's going to be all about air masses. We're going to have one about fronts, precipitation, and snow. Okay. Check. Air masses. An air mass is a large body of air with generally uniform temperature and humidity. The area over which an air mass originates is what provides its characteristics. The longer the air mass stays over its source region, the more likely it will acquire the properties of the surface below. As such, air masses are associated with high pressure systems. There are 2 broad overarching divisions of air masses based upon the moisture content. Continental air masses, designed by the lowercase letter c, originated over continents, are therefore dry air masses. Maritime air masses, designated by the letter M, so we can see like little m, little c, little m, little m, little m, little c, little c. These originate over the oceans and therefore are moist air masses. So that makes sense. The fact that continental they're going to be over the continents, and maritime is going to be over the marine, basically marina life, and that would be the oceans. Each of the divisions are then divided based upon the temperature content of the surface over which they originate. Arctic air masses, designated by the letter A, right here, are very cold as they originate over the Arctic or Antarctic, so it would be down here too, regions. Polar masses, designated by the letter P, so right here, are not as cold as the Arctic masses as they originate over high latitudes of both land and sea. And then we've got T. The tropical masses, designated by T, are warm-hot as they originate over the lower latitudes of both land and sea. Putting both designations together, we have, for example, a continental Arctic air mass designated by CA, which sources over the poles and therefore very cold and dry. Continental polar, CP, is not as cold as the Arctic air mass, but is also very dry. Maritime polar, MP, is also cold but moist due to its origination over the oceans. The desert region air masses, hot and dry, are designated by CT for continental tropical. As these air masses move around the Earth, they can begin to acquire additional attributes. For example, in winter, an Arctic air mass, very cold and dry air, can move over the ocean, picking up some warmth and moisture from the warmer ocean, and becoming a maritime polar air mass, one that is still fairly cold but contains moisture. If that polar air mass moves south from Canada into the southern U.S., it will pick up some of the warmth of the ground, but due to the lack of moisture, it remains very dry. This is called a continental polar air mass. Air mass boundaries. The motion of air mass motion is usually based upon the airflow in the upper atmosphere. As the jet stream changes intensity and position, it affects the motion and strength of air masses. Where air masses converge, they form boundaries called fronts. Fronts are identified by change of temperature based upon their motion. With a cold front, a colder air mass is replacing a warmer air mass. A warm front is the opposite effect, and the warm air replaces cold air. There is also a stationary front, which, as the name implies, means the boundary between the two air masses does not move. Okay, so here we can see cold is pushing in and pushing out the warm, and then warm front pushing out the cold. Okay. The motion of air masses also affects where a good portion of precipitation occurs. The air of cold air masses is more dense than warmer air masses. Therefore, as these cold air masses move, the dense air undercuts the warmer air masses, forcing the warm air up and over the colder air and causing it to rise into the atmosphere. So we can see how it's going up. So fronts don't just appear at the surface of the Earth, they have a vertical structure and slope to them as well. You can see that, right? Warm fronts typically have a gentle slope, so the air rising along the frontal surf is gradual, whereas this, it's more curved, so it's not going to be as that. With warm fronts, the gentle slope favors a broad area of rising air, so there is typically widespread layered or stratiform cloudiness and precipitation along and to the north of the front. The slope of cold fronts, being much more steep, forces air upward more abruptly. This can lead to a fairly narrow band of showers and thunderstorms along or just ahead of the front. There is also another boundary that exists, except this boundary divides most moist air from dry air, called a dry line. This boundary will separate moist air from the Gulf of Mexico to the east and dry desert air from the southwestern states to the west. It typically lies north-south across the central and southern high plains states during the spring and early summer. The dry line typically advances eastward during the afternoon and retreats westward at night. All right, so that is air masses. Go back. We can learn more about fronts. So we got an intro to fronts with air masses. Now we can learn more about them. All right. And we got some good pictures and all sorts of cool stuff. When a front passes over an area, it means a change in the weather. Many fronts cause weather events such as rain, thunderstorms, gusty winds, and tornadoes. At a cold front, there may be dramatic thunderstorms. At a warm front, there may be low stratus clouds. Usually the sky is clear once the front is passed. What is a weather front? A weather front is a transition zone between two different air masses at the Earth's surface. Each air mass has unique temperature and humidity characteristics. Often there is turbulence at a front, which is the border line where two different air masses come together. The turbulence can cause clouds and storms. Instead of causing clouds and storms, some fronts just cause a change in temperature. So think about whenever we get the cold, they always talk about a cold front, I feel like we always get one in November where suddenly it just gets really cold. It just causes a change in temperature. Okay. However, some storm fronts start Earth's largest storms. Tropical waves are fronts that develop in the tropical Atlantic Ocean off the coast of Africa. These fronts can develop into tropical storms or hurricanes if conditions allow. Fronts move across the Earth's surface over multiple days. Their direction of movement is often guided by high winds such as jet streams. Landforms like mountains can also change the path of a front. There are 4 different types of weather fronts: cold fronts, warm fronts, stationary fronts, and occluded fronts. So a cold front, which we learned a little bit about in our air masses one. A cold front forms when a cold air mass pushes into a warmer air mass. Cold fronts can produce dramatic changes in the weather. They move fast, up to twice as fast as a warm front. As a cold front moves into an area, the heavier, more dense cool air pushes under the lighter, less dense warm air, causing it to rise up into the troposphere. Lifted warm air ahead of the front produces cumulus or cumulonimbus, clouds and thunderstorms like in the image on the left. It's right here. As the cold front passes, winds become gusty, there is a sudden drop in temperature, and also heavy rain, sometimes with hail, thunder, and lightning. Atmospheric pressure changes from falling to rising at the front. After a cold front moves through your area, you may notice that the temperature is cooler. You may notice that the rain has stopped, and the cumulus clouds are replaced by stratus and stratocumulus clouds or clear skies. On weather maps, a cold front is represented by a solid blue line with filled-in triangles along it, like in the map on the left, right here. The triangles are like arrowheads pointing in the direction that the front is now moving. Notice on the map that temperatures at the ground level change from warm to cold as you cross that front line. So we can see like here it's 69, 70, 72, but you guarantee that once this hits, it's going to be down in like the 50s. So warm fronts. Also, we learned about these in our last one. A warm front forms when a warm air mass pushes into a cooler air mass, shown in the image to the right, A. Warm fronts often bring stormy weather as the warm air mass at the surface rises above the cool air mass, making clouds and storms. Warm fronts move more slowly than cold fronts because it is more difficult for the warm air to push the cold, dense air across the Earth's surface. Warm fronts often form on the east side of low-pressure systems where warmer air from the south is pushed north. You will often see high clouds like cirrus, cirrostratus, and middle clouds like altostratus ahead of a warm front. These clouds form in the warm air that is high above the cool air. As the front passes over an area, the clouds become lower and rain is likely. There can be thunderstorms around the warm front if the air is unstable. On weather maps, the surface location of warm front is represented by a solid red line with red filled-in semicircles along it. Like in the map on the right, B. So right here. All right. The semicircles indicate the direction that the front is moving, so it's moving this way. Okay. They are on the side of the line where the front is moving. Notice on the map that the temperatures at ground level are cooler in the front of the front than behind it. So here we know that this is pushing through. It is warmer over here. This side is a little bit cooler, but it's going to get warm. Now you can also have a stationary front. A stationary front forms when a cold front or a warm front stops moving. This happens when two masses of air are pushing against each other, but neither is powerful enough to move the other. Winds blowing parallel to the front instead of perpendicular can cause it to stay in place. A stationary front may stay put for days. If the wind direction changes, the front will start moving again, becoming either a cold or warm front, or the front may break apart. Because a stationary front marks the boundary between two air masses, there are often differences in air temperature and wind on opposite sides of it. The weather is often cloudy along a stationary front, and rain or snow often falls, especially if the front is in an area of low atmospheric pressure. On a weather map, a stationary front is shown as alternating red semicircles and blue triangles, like in the image at the left. Notice how the blue triangles point in one direction and the red semicolors point in the opposite direction. And then we have our air. Okay. The final front is the occluded front. Sometimes a cold front follows right behind a warm front. So we got warm front, cold front. All right. A warm air mass pushes into a cooler air mass, the warm front, and then a cold air mass pushes into the warm air mass, the cold front. Because cold fronts move faster, the cold front is likely to overtake the warm front. This is known as the occluded front. So right here. At an occluded front, the cold air mass from the cold front meets the cool air that was ahead of the warm front. The warm air rises as these air masses come together. Occluded fronts usually form around areas of low atmospheric pressure. There is often precipitation along an occluded front from cumulonimbus or nimbostratus clouds. Wind changes direction as the front passes and the temperature either warms or cools. After the front passes, the sky is usually clear and the air is drier. On a weather map shown to the left, an occluded front looks like a purple line with alternating triangles and semicircles pointing in the direction that the front is moving. It ends at a low pressure area shown with a large L on the map, begins at the other end when cold and air fronts connect. Okay. So those are the different fronts. Now we have types of precipitation. I really hope you guys have this worksheet, so that way you guys aren't just listening to my voice talk about nothing. So types of precipitation. We have rain, which is the most commonly observed. Drops are larger than a drizzle and are considered drops that are larger than a drizzle are considered rain. So we know what raindrops look like. Okay, so you guys are familiar with rain, but you can see here in the picture, rain is really, they're bigger. Okay, now a drizzle is fairly uniform precipitation composed exclusively of fine drops very close together. Drizzle appears to float while flowing air currents, but unlike fog driplets, it falls to the ground. Quite often, fog and drizzle occur together. So, like, you might see more of a drizzle. Like, I tend to see the drizzle, like, in the morning, whereas, like, rain will happen anytime, right? We have ice pellets, or known as sleet. We sometimes get these, in the winter months. So precipitation of transparent or translucent pellets of ice, which are round or irregular hard grains of ice consisting of frozen raindrops or largely melted then refrozen snowflakes. Hail. I can't remember the last time we really had like hail, like where it was like this big of hail. I think it's been a while, but I know we do get hail at least once every year. So precipitation in the form of small balls or other pieces of ice falling separately or frozen together in irregular lumps. Associated with thunderstorms, individual hailstones are about 1/4 of an inch or greater in diameter. Hail sizes of 1 inch or more are indicative of severe thunderstorms. So if you got golf balls falling from the sky, it's a severe thunderstorm. Small hail, or snow pellets, precipitation of white grains of ice that are round or sometimes conical. These are less than 1/4 of an inch. So if it's 1/4 of an inch, it's hail. If it's less, it's snow pellets. And then snow, we all know what snow is, but that is the precipitation of snow crystals. We get the form of the 6-pointed stars, even though all snowflakes are different. Snow grains. This is very small white and opaque grains of ice, basically a frozen drizzle. Ice crystals generally occur in very cold regions. They are falling crystals of ice in the form of needles, columns, or plates. This is also called diamond dust. Ice crystals appear like fog with individual water particles forming directly as ice. The shape of the individual ice crystals causes the light pillar optical effect above the light source. Right? So those are the different types of precipitation. And then the final slide is a closer look at snow. Okay. Alright, so how snow forms. Snow in the atmosphere. Whether winter snows produce snow relies heavily on the temperature, but not necessarily the temperature we feel here on the ground. Snow forms when the atmosphere temperature is at or below freezing, 0 degrees Celsius or 32 degrees Fahrenheit, and there is a minimum amount of moisture in the air. If the ground temperature is at or below freezing, which is 32 degrees in Fahrenheit, or 0 in Celsius, the snow will reach the ground. However, the snow can still reach the ground when the ground temperature is above freezing if the conditions are just right. In this case, snowflakes will begin to melt as they reach this higher temperature layer. The melting creates evaporative cooling, which cools the air immediately around the snowflake. This cooling retards melting or slows it. As a general rule, though, snow will not form if the ground temperature is at least 5 degrees Celsius or 41 degrees Fahrenheit. While it can also be too warm to snow, it cannot be too cold to snow. Snow can occur even at incredibly low temperatures as long as there is some source of moisture and some way to lift or cool the air. It is true, however, that most heavy snowfalls occur when there is relatively warm air near the ground, typically -9 degrees Celsius, 15 degrees Fahrenheit, or warmer, since warmer air can hold more water vapor. Because snow formation requires moisture, very cold but very dry areas may rarely receive snow. Antarctica's dry valleys, for instance, form the largest ice-free portion of the continent. The dry valleys are quite cold but have very low humidity, and strong winds help wick any remaining moisture from the air. As a result, this extremely cold region receives little snow. Snow on the ground. The character of the snow surface after a snowfall depends on the original form of the crystals and on the weather conditions present when the snow fell. For example, when a snowfall is accompanied by strong winds, the snow crystals are broken into smaller fragments that can become more densely packed. After a snowfall, snow may melt or evaporate, or it may persist for long periods. If snow persists on the ground, the texture, size, and shape of individual grains will change even while the snow temperature remains below freezing, or they may melt and refreeze over time and will eventually become compressed by subsequent snowfalls. Over the winter season, the snowpack typically accumulates and develops a complex layer structure made up of a variety of snow grains, reflecting the weather and climate conditions prevailing at the time of deposition, as well as changes within the snow cover over time. So I'm thinking that this is like, you know how we get like powdered snow, and then you also get that one type of snow that is like perfect for snowballs because there's just a little bit of ice to it. We're just talking about different kinds of snow. So how big can snowflakes be? Because I know we've seen some pretty big snowflakes. Snowflakes are accumulations of mini snow crystals. Most snowflakes are less than 1.3 centimeters or a half an inch across. Under certain conditions, usually requiring near freezing temperatures, light winds, and unstable atmospheric conditions, much larger and irregular flakes can form, nearing 5 centimeters, 2 inches across. No routine measure of snowflake dimensions are taken, so the exact size is not known. Cool. So from those different readings, you would be able to answer all 17 of these questions, because all 17 of these questions are what, how, why, and it's all stuff that is right through that. So you probably were able to complete these questions while I read. All right. All right, so that's 30 minutes. Okay. So that would be that one. Okay. That would be NTI assignment number 1, which I'm pretty sure you all have. All right. Now, NTI assignment number 2, I'm not 100%, but at the same time, I feel pretty confident that I don't think you guys have this assignment. I'll pull up the map so you guys can at least kind of see. Obviously, this does require you to have access to a computer because it is focusing on, hey, you have to make sure that you follow this and do the things that it tells you to. So if we go to this mapmaker website, let's get going. Now we go to our base maps. So if you see, I can do this fun little thing. Base maps is right here. We click base maps. Now we got lots of different maps, but what we want is ocean. All right, so now we get this nice little ocean map that we have set up. And we do need to kind of zoom out just a little bit so that way you guys can see the whole world, right? Because we want to be able to see the whole world. Now, downside is this is going to kind of repeat itself. I don't think I can. I want to just zoom in a little bit more, but I want you guys to be able to see like there's Antarctica and stuff. All right, we'll just go this way. Now we have to add layers. And according to Ms. Stoltz, we need to add the layer of underwater and ocean surface currents. Now, I'm going to make this nice and bigger so that way we can really see. If we look at our legend, it tells us that the blue arrows are cold water and the red arrows are warm. Now, it kind of makes sense because one of your assignments is write out 3 observations. Well, what do you guys notice about these arrows? Where are they at? We see a lot of blue arrows, which tells us cold water currents. We see a lot of that near what? And does that make sense that cold water would be found near the South Pole? If we scroll up, here's North Pole. Look at that. We got blue again. Okay. Whereas right around here where the equator's at, we have a lot of red. Okay. So thinking about that, what does that tell us? What's an observation we can make? So you would do that. Now we can add the climate zones. So we just are going to add another layer. We're going to click on climate and weather and climate zones. We can press done. Now we have the climate zones. We go to our legend and it tells us exactly what each of these things means. So like Kentucky is around here. We are in this dark green. This dark green, humid temperature climate, no dry season. All right. We look around here. We got Africa. Hey, it's that really light one. Dry climate, arid. I'm from Arizona. Arizona's right over here. Same thing. Okay. Southern California, dry summer. So we just have where you guys could look at this map and see specifically what the climate zone is. Now your assignment asks you to write 3 different observations. So what do you guys notice? Where is this cold climate at? How does this all look? Does it kind of mirror itself? We've got a lot of this, like these are all kind of in the same area, but hey, Australia for some reason has the same setup as up here, but yet it's all the way down here. So how does that make sense? Okay, you guys could record those notes. The last part, what are two inferences? And remember, inferences are just, they're educated guesses. These are guesses that with the information provided for you, you know, what can you assume or say about that? Okay, it may not be 100% right, but you're using evidence to explain it. So here, an inference I would make is, you know, I noticed that where the equator would be is where we have these different, we have the weather that says humid equatorial climate. You know, we can see where, boom, it's all kind of right in a line. Hey, there also happens to be a lot of warm water in that section. So that would make sense because at the equator, not only should the climate be warmer, the water should also be pretty warm. Okay, so that would be an inference I would make. So now you think about looking at this map, what sort of inference would you make? Like I said, I don't think you guys have this. I can make a second video about this information with this second website, but I kind of feel like you guys don't have this. But it is a pretty cool map to look at, and like I said, if somebody's like, hey, Miss Lloyd, yeah, we definitely have that worksheet, I will talk about the second half, okay? But the nice thing is if you're like, I'm not gonna wait for Miss Lloyd, you can just go ahead and you can follow all the fun stuff that Miss Stoltz spelled out for you. All right, these are super user-friendly websites, okay? So we've got this, and we can just kind of go from there, okay? Click on your birthday, choose an additional date, you get to do all that cool stuff, okay? All right, I'm going to end this video here just because it is already about 30 minutes, and I told you guys I was going to try to keep my videos down to 30 minutes. After, I actually have to go to a meeting, but after that, I will do a video about the next few assignments, okay? So, stay tuned. I will talk more, and I'll go over these next few things as well as the second packet. So you should expect about 3 different science videos from me today. All right? Bye, guys.